to us. So consider a steam power plant operating and the ideal Rankine cycle. Whatever that steam power plant is operating under the ideal Rankine cycle. Okay, so here operating cycle is given Rankine cycle. Okay, so the steam enters the turbine at 3 megapascal. Okay, so what they have given to us, the steam enters the turbine, so entry for the turbine at 3 megapascal. So pressure is given, that pressure is a 3 megapascal. Okay, and 350 degree. Okay, so entry for the turbine, steam entry for the turbine, so its properties are given. That properties are its pressure 3 megapascal and its temperature is 350 degree centigrade. Okay, and is condensed in a condenser, and then again after that, that steam is condensed in a condenser. Okay, after the that process of expansion, that steam is condensed in a condenser at a pressure of 75 kilopascal. Okay, so the pressure of that condenser pressure, it is given 75 kilopascal, and the steam entry for the turbine, that pressure is given 3 megapascal. Okay, so they have asked to us determine the thermal efficiency of the plant. Then what we have to find? Thermal efficiency of the plant, that we have to find. Okay, so before the finding all that parameter, that is the thermal efficiency for that plant, here we are going to see the TS diagram. Okay, here is the TS diagram for the Rankine cycle. Okay, so the first if we see the first process, that is process 1 to 2, here is that process 1 to 2. During process 1 to 2, what happened, that is the it is the isentropic process. First thing is that it is the isentropic process, and it is isentropic expansion process. Okay, so as it is isentropic expansion process, so 1 to 2, whatever the line 1 to 2, it is exactly straight line. Okay, now 2 to 3, if we see the process 2 to 3, so 2 to 3, it is a condensation, that means conversion of that steam into water. Okay, now 3 to 4 process, which one is the 3 to 4 process? During 3 to 4 process, that is the, it is the isentropic compression of that fluid. Okay, so its pressure increases, whatever the fluid's pressure, that water's pressure, it is increases, but that process is at a constant entropy process. Okay, so where the entropy remains constant. So during 3 to 4 process, entropy constant. During 1 to 2 process, entropy constant. And during 2 to 3 process, pressure remains constant. So at constant pressure, that condensation will happen. Okay, now the 4 to 1 process, last process, 4 to 1 process. During 4 to 1 process, what is going on? During 4 to 1 process, that is the at constant pressure, heat addition takes place in the boiler. Okay, so conversion of that water into steam take place. Okay, so that after that conversion of water into steam, that steam is going in superheated region. That's why that point is in a superheated region. Okay, how we have decided that point is in a superheated region? By reading the properties of that steam, because the pressure of that steam, it is 3 megapascal and its temperature is 350 degree centigrade. Okay, so if we see for 3 megapascal, if we consider the condition, that is saturated steam. If our steam is saturated, then that steam should be on vapor line. Okay, that steam is on a vapor line, but our temperature, it is 350 degree centigrade, so temperature, it is greater for that condition. Which condition? For 3 megapascal, our pressure, I think it is up to 320 degree centigrade, but it is beyond that. That's why that point it is in a superheated region. Okay, by reading the steam properties from the steam table, we have decided that. Okay, so our point 1, it is in a superheated region. Okay, now here we are going to write down first of all the given data. After that, we are going to find the unknown quantity of our problem. Okay, so in given data, what we have given, steam enters turbine at 3 megapascal. So entry point, that is the point number 1. Here is our point number 1. Okay, so entry steam is enters at 3 megapascal. So here I am writing PB, that is the boiler pressure. It is a boiler pressure, because whatever the steam coming out from the boiler, that should be entry for the turbine. That's why here I am writing PB, it is equals to 3 megapascal. Okay, now we know, for we know already 1 bar is, it is equals to, okay, already we know 1 bar, it is equal to 10 raised to 5 pascal. That means 10 raised to 5 Newton per meter square. Okay, so 1 bar is equal to 10 raised to 5 pascal, that means 10 raised to 5 Newton per meter square. But here we have given PB, that is boiler pressure, that is the pressure, entry pressure for the turbine, 3 megapascal. So we can convert that 3 megapascal into bar. How we can convert that? As we know, 3 megapascal. Okay, so mega means 10 raised to 6. Okay, mega, that means it is a 10 raised to 6. That's why here we can see 3 into 10 raised to 6 megapascal. Okay, we have written that. Okay, now we have to convert that mega into bar. How can we can convert? Just we have written that 30. Okay, instead of 3 we have written 30. Okay, into 10 raised to 5, because we have taken here 0, in front of 3 we have taken 0, so it becomes 30 into, instead of 10 raised to 6 now it becomes 10 raised to 5, and it is a pascal. Okay, now as we know, 1 pascal, that is the 1 bar, that means it is 10 raised to 5 pascal, so it becomes 30 bar. Okay, that means 10 raised to 5 pascal, it is equals to 1 bar, so it is becomes 30 bar. Okay, so why we have converted that value into bar? Because if we have given stream table it is in a bar, then that's why we have converted that. Okay, that's why we have converted that value. Okay, so at that condition, for that state also we have given, what we have given, also for that condition we have given 350 degree centigrade temperature. So here we have written 350 degree centigrade temperature. Okay, so this is the property for the state 1. Okay, now second value that they have given to us, what they have given to us, and is a condensed, that steam is condensed in the condenser, the steam is condensed in a condenser at a pressure of 75 kilopascal. Okay, so that pressure it is given 75 kilopascal. Okay, how much that pressure is given? It is a 75 kilopascal. Okay, so here is that condition for the state number 2 after condensation. After that process, which expansion process. So after expansion that steam will come inside that condenser, so that pressure, that is means condenser pressure we have given, and that is 75 kilopascal. Similarly we can convert that 75 kilopascal into bar. So after that conversion, that means 75 kilo means it is 10 raised to 3. Okay, kilo means that is 10 raised to 3. Okay, so here is that value, kilo, 75 kilo means 10 raised to 3 pascal. Okay, so we have converted that, we have to convert that into bar. So we have converted here that into bar, that means it is a 0.75 bar. Okay, 75 kilopascal, we have converted that into bar, it is 0.75 bar. Okay, so what we have given, what given data is given to us, that given data is for state number 1 pressure it is 30 bar, for state 2 pressure it is 0.75, that means it is first is a boiler pressure and second one is a condenser pressure. Okay, now for state 1 we have given temperature it is 350 degree centigrade. Okay, now what they have asked to us, if we see the problem, they have asked to us find the thermal efficiency. Okay, what they have asked to us, find the thermal efficiency, that means we have to find efficiency. Okay, efficiency value that we have to find. To before finding before we have to find efficiency, first of all find the values, that is different enthalpies for the different state. That means we have to find the values of H1, then H2, similarly H3 and H4. These four values we have to find. After finding these four values, definitely we will get the value for the efficiency. Okay, so here we are going to find these values. Okay, so we have given the properties. By using that properties, which properties we have given, let we have to see here. So the so specific enthalpy at the pressure 30 bar and temperature 350 degree centigrade. Okay, for 30 bar pressure and 350 degree centigrade temperature, from steam table we will get these values. That is the for state number 1 we will get enthalpy H1, it is a 3117.5 kilojoule. That value we will get from that properties. Which property? From pressure and temperature property for the state number 1. Okay, so that value we will get H1 equal to 3117 kilopascal. Now second, specific entropy, we can find the second value, that is specific entropy for that same property. That is specific entropy for the state 1, it is S1 equals to, for same 30 bar and 350 degree centigrade temperature, it will get 6.747 kilojoule per Kelvin. Okay, so we have got the two values H1 and S1 for the state 1. Okay, from the given properties. Okay, now next how we will get that values? Here is that steam table. So from steam table, if our pressure is 30 bar, okay, if our pressure is 30 bar and temperature is 350 degree centigrade, okay, temperature it is 350 degree centigrade, so for that we will get enthalpy, it is 3117.5. okay, for pressure 30 bar and temperature 350 degrees centigrade, we will get entropy. Directly we will get that entropy value is 6.747. Okay, it is kilojoule per Kelvin. Okay, that value we will get from superheated steam table. Okay, from that table we will get directly that values. Okay, now here what we have got the value, only we have got H1. Okay, now we have to find H2, H3 and H4 also. Okay, after finding all these value, definitely we will get the efficiency. Okay, now as we know process 1 to 2. Okay, process 1 to 2, here is that process 1 to 2. Process 1 to 2, it is a constant entropy process, that is isentropic expansion process in a turbine. So that means S1 equals to S2, that is the entropy remains constant. So here that's why here I have written that is S1 equal to S2. Okay, now S1 value, already we know the value of S1. Okay, S1 is already known, here is that value S1, it is 6.747. Okay, but we don't know SF2, X2 and SFG2. Okay, so we have to write the formula here, S1 equal to S2. So S1 equal to SF2. S2 means what? It is the standard formula, it is here is that formula, SF2 plus X2 into FCFG2. This is the formula. Okay, now here only we only know the value of S1. Okay, now from steam table again. Okay, if we see the point number 2. Okay, here is that point number 2. So here is that state. Okay, here is that point number 2. That point number 2 or for state 2 we have an pressure of 75 or 0.75 bar. That value it is 0.75 bar. So from steam table, from steam table at 0.75 bar we will get the value SF2, it is, that is SF2 equal to 1.217. Okay, 1.217, and SFG2 we will get 6.235. Okay, from steam table we will get that values 6.235. Okay, now after putting these two values. Okay, now put the value of S1 here. Okay, now SF2, here already we know the value of SF2, here already we know the value of SFG2. Okay, put that values. After putting these two values we will get the dryness fraction, and that dryness fraction will be X2. Okay, and it is equals to 0.87. After solving that we will get that answer, X2 equal to 0.787. Okay, we will get that answer. Okay, why we have find here X2, value of X2? Because already we find the value of H1. To find the value of H2 we have to know the value of X2. Okay, to find the value of H2 we have to find the value of X2. That's why we have find out the value of X2. Okay, now the next, now we will get the value of H2. Okay, here is that value. Now H2 is equal to, you know the formula to calculate H2, H2 equal to HF2 plus X2 into HFG2. Okay, this is the formula to calculate H2. Okay, so for pressure 0.75 bar. Okay, for pressure 0.75 bar. Okay, for 0.75 values of enthalpies are, and these values are HF2 equals to 385.9 kilojoule. Okay, and value of HFG2 it is 2277.7 kilojoule. Okay, these two values, how we will get these two values? From steam table at a pressure 0.75 bar. Okay, now put these two values in this formula. After putting these values, here is the value of H2. So H2 equal to, here is the value of HF2 385.9 plus this is the value of X2. X2 already find out that value, it is 0.87. Okay, it is 0.87. Now the value of HFG2 it is 2277.7. Put that value. After putting that value we will get the value of H2. Okay, and that value will be 2367.49 kilojoule. Okay, this should be the value of H2. Now we got the value of H1 and H2. Now we can find the remaining values. That values are H3 and H4. So how we will get that values? Okay, so at 0.75 bar. Okay, at 0.75 bar. Okay, for that it is a condensation pressure. So for that condensation pressure, value of H3. Okay, actually H3, if we see the H3 or the state 3. Okay, here is that diagram. If we see the point 3, okay, H3, here is that point H3. Okay, that point H3, okay, that point H3 is on saturated line, saturated liquid line. Okay, it is directly on saturated liquid line, that 3 point. That's why for the pressure which pressure? 0.75 bar. For 0.75 bar, that is the condensation pressure, we will get directly the value of H3, because that point state number 3, it is on a saturated liquid line. So from steam table again we will get the value of H3 directly. H3 means it is the value of HF. H3 it is nothing but the value of HF, and that value it is 385.9 kilojoule. Okay, that is the value of H3. Okay, now we got the value of H1, H2 and H3. Okay, these three value we have got, H1, H2 and H3. Only the value one remain, that is the H4. After getting the value of H4, definitely we will get our final answer. Okay, so how we can find the value of H4? So before finding the value of H4, we know the work done. Okay, work done. Before finding that value, here is the work done by the pump. Okay, and that work done will be H4 minus H3. Okay, here is the pump. Okay, 3 to 4, it is isentropic compression of that liquid. So 3 to 4, it is a here entropy remains constant, and that work is a pump work. Okay, so we are adding that work. Okay, that is work in. Okay, so here, that's why here formula, pump work or work done by the pump, it is given by, it is H3 minus H4. Okay, now we know that is the pump work, it is given by, also the formula to calculate pump work, V3. Okay, it is state 3. Here is that from 3 to 4 process, it is the isentropic compression, that is a, here during 3 to 4 process there is an pump. Okay, so we are here, whatever that pressure, whatever that process take place, that process will take place at constant volume. Okay, that's why here V3 is there, V3 into P4 minus P3. Okay, because the that pump work will be from 3 to 4, that's why here P4 minus P3, which is equal to H4 minus H3. Okay, H4 minus H3. Now put the all values that we know. Okay, from steam table again, from steam table we will get the value of V3. So at 0.75 bar we will get the value of V3, it is 0.001038. That should be the value of V3. That is, V3 means it is value of VF. V3 means that is the value of VF, because that state 3 or point 3 is on a saturated liquid line, that's why. Okay, so we will get that value, that is at 0.75 bar from steam table, V3 equal to 0.01038. Okay, now put that value of V3 here. Okay, V3. Now we know the P4. P4 is nothing but, if we see that diagram, here is the P4. Okay, here is that P4. P4 is nothing but boiler pressure. Okay, for that state 4 or point 4, it is a boiler pressure, and we know that boiler pressure it is 30 bar. Okay, that pressure it is a 30 bar. So here we are writing it is 30 bar. Okay, it is 30 bar. And what about P3? P3 it is condensation pressure, and that should be 0.75. Okay, and as it is bar, that's why here we have to write down 10 raised to 5. Okay, now in next bracket, which is equals to H4 minus H3, already we know the value of H3. Okay, now put that value, and which is in kilojoule. Now solve that. After solving, we will get the final value, that is H4. Okay, and that H4 is given by 388.9. This is the value of H4 kilojoule. Okay, 388.9 kilojoule, that is the value of H4. Okay, now here we got the all answers, all the values, that is H1, H2, H3 and H4. Okay, now we have to find thermal efficiency. Okay, the formula to find that efficiency, it is given by net work done divided by heat supplied, QS. Net work done divided by heat supplied, that is QS. So efficiency equal to net work done divided by heat supplied. So net work done, it is given by turbine work minus pump work. So it is turbine work minus pump work. If we minus that difference between turbine work and pump work, that is the net work done divided by heat supplied, that is QS. So how we can find that turbine work? We know turbine work during process 1 to 2. This is the process 1 to 2. During that process, turbine work will be take place. So turbine work will be get H1 minus H2. Okay, during process 1 to 2. Now minus pump work, we know the pump work during process 3 to 4. During process 3 to 4, we will get the pump work. Okay, so that is H4 minus H3, we will get the pump work. So here H1 minus H2 bracket complete minus H4 minus H3 bracket complete divided by heat supplied, and we know the formula to calculate heat supplied. Heat supplied during the process, here is the process, that during process 4 to 1 heat is supplied. at a constant pressure. Okay, so heat is added in a boiler at a constant pressure, that so that water should be converted into a steam. Okay, so we will get that answer as H1 minus H4. Okay, now we know the value of H1, H2, H3 and H4. Put all these values. Okay, put all these values. Put the value of H1, H2 here, and H4, H3, H1 and H4. Okay, put all these values. Okay, put the value of H1, that is 3117.5. Then H2 it is 2367.49. Then minus H4 it is 388.9, and H3 it is 385.9. Okay, divided by H1 minus H4. H1 it is 3117.5 minus H4 it is 388.9. Okay, now after calculating all that, we will get our final answer, that is efficiency is given by 27.37%. That should be our final answer. This is our efficiency of the plant. Okay, thank you very much.